subway. Is on toll. So that. Someway.
Okay, so it's time to get started. Okay, so there's a few things we're going to talk about today. First, we're going to go over the basic operation of something called a shift register. We talked about a memory register already that's made out of D flip-flops. And the main purpose of a memory register is to store data. Well, there's this other type of register called a shift register, which is also made out of D flip-flops. That's primary purpose is to manipulate data by shifting bits from that first shift register sometimes. So we're going to go over the basic operation of it. Then I'll just talk about a few applications. I mean, there's many applications of the shift register, but I'll just talk about a few. And then we're going to go over a universal shift register, which is sort of an extension of a register. It's basically a combination of a shift register with a memory register. And this is important to know because this is part of the individual final project. Okay. And then the rest of the class is going to be on sequence detection, which is lab 6. Okay, you build an FSM that does sequence detection in lab 6. Okay, so after today's lecture, you'll be able to do lab 6 along with, you already have enough information to do lab 5. Okay, remember lab 5 is basically lab 4 with memory added and a time multiplexer that we provide to you that Dr. Mealy designed that enables us to put data on all 4 7-segment displays at the same time. And I just wanted to give a note, actually a couple of notes here. One I have written up here about lab 5, because I don't think I mentioned this last time. And that's in lab 5, if you look at the instructions, it specifically says that for the clear input and also the enter input, to use buttons, okay, instead of switches. So, you're still going to use switches for, the sub and, A and B inputs. But for these 2 inputs that have to do with the memory, the clear and the enter, we want you to use buttons that are on the basis board. There's 5 buttons, and you can just pick any 2 of those 5, get use of those 2. And, the way you do that is just in your constraints, there's a section for switches, there's a section for LEDs, there's a section for the 7-segment display. There's also a section for buttons. Okay, so you just assign those inputs to, like I said, any 2 buttons you want. Okay, the other thing about lab 5 that I don't think I mentioned is that the clock input, you have to map your clock input to the board through the constraints file. And the way you do that is, if you look at the very top of the constraints file, there's like 3 lines that have CLK, it's lowercase CLK. You just uncomment those top 3 lines. And that way, as long as you name your clock CLK, and I would highly recommend that for all your clock inputs, just use CLK and make it lowercase because the constraints file is case sensitive. But if you use uppercase CLK, it won't match up. You'll get errors. Okay. So yeah, those 2 things I just wanted to make a note of because I don't think I mentioned them last time. Okay, but they were in the instructions. All right. So like I said, we're going to start off with what a shift register is, and then how it, its basic operation. So first of all, there's 2 types of shift registers. Okay, SRR stands for shift right register, and SLR stands for shift left. Okay, so shift left. Okay, what we mean by a shift right is that data on data input. Okay, and here, of course, data is 0s and 1s. So, this could be a 0 or a 1. Well, whatever we have on, whatever data we have on the data input, it goes into the most significant bits of the shift register. Okay, so shift right means data on the data input goes into the most significant bit of the shift register. So based on this definition of a shift right, what do you think a shift left is?
Just killing the policeman.
Right, exactly. So a shift left, it's just, data on the data input goes into the least significant bit of the shift register. Okay, so that's what distinguishes between the two types, is just where the data in goes to. Yeah, either the most significant of the shift register or the least significant. So let's look at a couple of examples. Okay, so above the line, this is a shift right example. Now, shift registers, just like memory registers, just like any type of device that's sequential, that has a clock input, it's either rising edge or falling edge. Okay, so, you can have a shift right register that's rising edge, or you can have one that's falling edge. For this example, we're going to use rising edge. Okay, and remember, that's the 0 to 1 transition of the clock, right? Okay, DR in, that's our data in when we're doing a shift right. So this is the data, the bit that's going to go into the most significant bit since it's shift right. Okay, now, this is the first time I think I've used this symbology, but you see this rectangle with the squares? This is shorthand notation for a register. Okay, remember, a register is just a collection of flip-flops, right? You need a flip-flop per bit. So whether you have an 8-bit memory register or whether you have an 8-bit shift register, you need 8 flip-flops. So this notation is in place of drawing a diagram that has 8 D flip-flops. Okay, I don't want to draw that diagram again. So I use this notation that represents that diagram. Okay, so the rectangle represents the collection of flip-flops, and then each square within the rectangle represents an output of one of those flip-flops. So, this is the output, the Q output of the least significant bit flip-flop. This is the output of the next one to the left, and so on. Okay, so just picture that this is representing 8 D flip-flops. Okay, see, the only difference between a shift register and a memory register is how the flip-flops are connected together. Okay, that's the only difference. They're both made out of flip-flops, but depending on how they're connected, you either get a memory register or a shift register. Okay, so you can see that this is our least significant bit, and this is our most significant bit of the register. And what you see, the data, the bits that you see inside the rectangle here, that represents the initial content. Okay, so initial contents of the shift register. Okay, that data was previously loaded in. All right, so now we're going to do a shift right, and we're going to shift right this 0. Well, the shift occurs on a 0 to 1 transition of the clock. Okay, so we have our clock input. And at the time of that 0 to 1 transition of the clock, that's when the shift is going to happen. So at this time, this 0 that's on the data in, this is going to go into the most significant bit of the shift register, and all the other bits shift over in one place. So this 1 will now be here. This 1 will now be here. This 0 will now be here. This 0 will now be here. This 0 will now be here. This 1 will go here. This 1 will go here. And then this 0 falls off the face of the earth. Okay, because there's nowhere for it to go. There's not a flip-flop for that. So it just goes away. You lose that bit. Okay, so you see, if we start off with these, or if we start off with this data in our shift register, and we just do one shift to the right will end up with this after this clock edge. Okay? Now, the important thing to realize again is that what makes it a shift right is the fact that this data is going into the most significant bit. Because of the way that I oriented this register, where I put the most significant bit furthest to the left, like normally we think of it, well, that's why it's called a shift right? Because the data comes in, everything else moves to the right. But even if I orient this shift register where it's vertical, where the most significant bit is on the top, the same operation applies. It's just the bits would be moving down, but we don't call that a shift down. Okay, it's a shift right because of where that data goes. It goes to the most significant bit, no matter how this register is oriented. Okay, so when you take a future class and they show shift registers vertical, you're not going to tell your instructor, oh, that's a shift down, right? Because there's no such thing as shift down or shift up or shift sideways or 45 degrees or whatever the orientation is. Okay. All right. So let's do a shift left example. Now, just to be different, I made this shift left a falling edge. So the shift left is going to happen on the 1 to 0 transition of the clock. Okay. And at the time of that 1 to 0 transition of the clock, this data on the input is going to go into the least significant bit. So again, this shows the initial contents. Okay, so now at the time of that 1 to 0 transition of the clock, this data, this 1 on the data input, it's going to go into the least significant bit. And then all the bits shift one place over. 0, 1, 1, 0, 0, 1. And then this 0 here, the most significant bit of the initial contents, that would be lost. Okay, there's no place for it to go. So it's just lost. Okay, so you see if we start with this data initially, we do 1 shift to the left where we're shifting in a 1. This is what we would end up with after this clock transition. Okay, so that's the basic operation of a shift right or a shift left. Any questions about this? You're going to get lots of practice with this because the activity today is, you need to know this for the activity. Okay, well, let's talk about some uses of a shift register. One use is that you can either do a multiply by a whole number power of 2 or a divide by a whole number power of 2 pretty easily. Because let's say we start off, let's say we start off with this data, the contents of our shift register. And let's say that we're treating these zeros and ones as an unsigned binary number. So what would this equal in base 10 if we're treating it as unsigned, where this is the ones column? What is it? A 12, right? Because we got a 4 and an 8. So you see this would be 12 in base 10. Well, if I now do a shift to the left and I bring in a 0, after that shift left, bringing in a 0, I would have this as my contents in my shift register, right? Because the 0 would come into the least significant bit since we're shifting left. And all the other bits would move over one place. So what is this in base 10? This is an unsigned binary. Yeah, it's 24 because we have an 8 and a 6, an 8 and a 16. So you see, I did a multiply by 2 by just shifting one place to the left and bringing in a 0. Okay, you got to bring in a 0, right? Because if you're bringing a 1, it's not a times 2. Okay. If I shifted a second time to the left and brought in a 0, what would I have? 48. Right? So you see, you can get a times 4, right? If you shift 2 places to the left, bringing in zeros. So every time you shift to the left, you get another multiply by 2. Okay, so you can multiply by any whole number power of 2 just by shifting the appropriate number of places to the left while bringing in a 0. So how do you think we would divide by a whole number power 2? Just shift the other direction and bring a 0 in, right? So if you did a shift right, you would do a divide by 2. So again, if we start off with a binary 12, and now I do a shift to the right, bringing in a 0, I would end up with a 6.
Like signed addition, are there cases where this is only valid if data starts falling off?
Yeah, that's, very good point. That, you can imagine here, if I did another shift to the right one place, I'd get 3. But then if I did another shift, right, I would lose that least significant bit and it would be 1, which wouldn't work. So you just got to make sure that your shift register will hold, the total number of bits that whatever you're looking to do. So you do have to watch out for that. That's true. In CP233, when you build a microprocessor, that microprocessor in CP233 has 32-bit shift registers. Right? So you get 32 bits. So plenty of bits. Okay, but it's the same, same thought process, no matter how many bits you have. Just more bits. Okay, another thing that you can do with shift registers that you might find interesting is, let's say, you have multiple 7-segment displays, like what's on your basis board, right? There's 4 of them. And remember we talked about that these 7-segment displays have an AN input. What does AN stand for again? And remember we talked about how you need a 0 on the ANO input in order for the display to light, right? If it has a 1, it's going to shut off. Well, you could do something like this with a shift register. Like maybe you have a 4-bit shift register, and initially you put the data 1110, and you connect this Q output of the shift register to that AN, and the Q output of this to this AN, Q output of that to that AN, and the Q out of this least significant bit of the shift register to the furthest to the right display. And maybe you make your data in equal to a 1. So initially, if this is your initial contents of the shift register, this furthest to the right display would be the only display that would light, right? The ones that have a 1 would all be off. And if I do a shift to the left and my data is equal to a 1, well, at the time of the clock edge, and let's say this is rising edge, okay, rising edge trigger shift register. Well, at the time of the 0 to 1 transition of the clock, the shift would happen. So this 1 would come into this least significant bit. This is our least significant bit here. All right, so the data in, the 1 would come in here, the other bits would all go one place over. Well, now after this first clock pulse, now this 7-segment would light and the other 3 would be off. All right, if I do another clock pulse with the same data in being a 1, so I do another clock pulse. Well, after that second clock pulse, I would now have this. So now this segment is powered, the other 3 are off. And then if I do a third clock pulse, again, keeping the data in at a 1, well, now this segment would light up and the other would be off. So what this effectively would do would cause like a scrolling message, right? Because, if I had a G going to this 7-segment, and I had an A going here and an R, probably be kind of hard to see an R, and then a Y, let's say. Well, first you would see the G, then a clock pulse later, you'd see the A, then a clock cycle later, you'd see the R, and then a clock pulse later, you see the Y. And if you pick the right clock frequency, this would look like it was scrolling, right? GAR, you can keep going if you have more displays. So, like you'll see at the stock market sometimes, watch like CNN or one of those cable shows, you'll see the ticker tape, the electronic ticker tape, and it looks like the message is moving along. Well, the data is always there. It's just, it looks like the message is moving because they're using a technique like this. Like you're only seeing this letter, then this letter, then this letter, then this letter. And again, they do it at a frequency where it looks like it's scrolling. Okay, so that's another use of a shift register. I mean, there's many other uses. These are just a couple that come to my mind, pretty quickly. You'll see another use of the shift register when you do the final project individual, because the final project individual is you're taking two 4-bit binary numbers and you're multiplying them together. And you'll see that shifting is part of a way that you can do binary multiplication. And I'm going to talk in more detail about that Tuesday of next week. Okay. All right. So any questions up to this point before I move the camera? We talk about a universal shift register. Okay, so everything's going all right so far. All right, let's move this over. Oh, I lost my little marker over here. What happened? It was like a little tie. I don't know, it was like a sandwich bag tie thing, and it walked away. But okay, we'll have to improvise here. Oh, actually, it's right there. All right. Okay. All right, so like I said, what we talked about up to this point, this is like basic shift register. A more practical, what you see more if you're really going to do something in the real world, so to speak, is this universal shift register. Okay, universal shift register, it can do a number of things. It can shift left. It can shift right. It can store, and you can load it. So really, a universal shift register is like the combination of a memory register along with the shift register, because you can shift the bits like a shift register, and you can also store and load like you do with the memory register. So it's kind of like 2 in 1. Okay. Here's the high-level black box diagram of a universal shift register. It has a D input, just like a memory register does. You can see here it's 8 bits. It has a Q output, 8 bits again. We got a clear input. Of course, we have a clock, right? Any sequential circuit, right? Registers, flip-flops, anything that's sequential that has memory is going to have a clock. And then it has this select input. Okay, this SEL, just like a MUX has a select. Now, remember, the MUX select is choosing between 2 data or a number of data inputs. And only choosing one of those to be connected to the output. Here, the select is doing something different. Okay, and you can see that it's 2 bits. So if I have 2 bits, how many values can I represent with 2 bits? 4, right? So that's the old 2 to the 2, right? The 2 to the number of bits gives you the number of values. So that means this select, I can choose from 4 things. So the next thing is to look at, on each table, there should be a handout that has this code on it. I only put 1 on each table. I didn't have enough for everyone. But take a look. You can kind of look together on your table or take a picture of it. This is the System Verilog code to model a universal shift register. And you're going to use this, like I said, in the final project individual, part of a 4-bit binary multiplier. So up at the top, you should be familiar with that, right? Because those are where your inputs and outputs are declared. Then we have an always FF block, right? You've seen an always FF block now a couple of times because that was part of the D flip-flop and also the register. It's also a portion of the FSM code. And you can see here that it's rising edge triggered, right? Because the always FF is sensitive to the positive edge of the clock. Now, this is a little bit different. With the FSM that we went over last class, in the always comb block of the FSM code, you had an if statement within a case, right? So you had like an if embedded in a case statement. Here you have the opposite, right? See here, a case is embedded in an if, right? So you see, you can have either. Sometimes you have an if within a case, sometimes you have a case within an if. So if you look at this, you'll see that, you know, if we clear, like if clear is active, well, then we're just going to make the Q output all zeros. Okay, if we're not clearing, then it's going to depend, you know, our output is going to depend on what we get from the case statement. Okay, so up at the board here, I just wrote down the else part of the if statement where the case is, because that's what I wanted to focus on. Okay, because the rest of the code, like I said, you're familiar with. Okay, so if we're not clearing, we now get to the else part of the if where the case statement is. And you see how the case statement is sensitive to the select input, right? Because remember a case, whatever's within the parentheses, when that changes, that's when the case gets evaluated. Okay, so like you said before, if we have 2 bits, we have 4 possibilities. So if you look at our case statement here, it starts with option 1. Okay, notice there's no option 0. We'll get to that later. But looking here at option 1, what is happening? Which one of these 4 things is happening if the select input is a 1, a binary 1? What is this when we're assigning Q to whatever the D input is? It's what? That's when we're loading. Right? Remember, storage is when the output remains what it was previously. Right? When we set Q to the D input, that's when we're putting the data into the register, right? So we're loading it. Okay, so this is load here. Okay, all right. Option 2, when the select is a binary 2. Well, let's look at the system Verilog here. We're assigning Q. You can see here Q bracket 6 to 0. So what that is remember, we number the least significant bit a 0, right? We always call the least significant the 0th bit. And then the most significant bit here would be 7 since there's 8, right? 8 bits. So the 6 to 0, that would be these 7 bits. And then you see a comma and you see a 1 tick mark B0. So you've seen this notation before. It was a while ago in class, but you've seen this notation with braces. Like in System Verilog, what's going on here when you have these 2 things separated by a comma within braces? There's a fancy word for it. You had an activity on that. Concatenation, exactly. And what does concatenation mean? Putting things together. Exactly, just joining things together, merging things together. So what's going to happen here is that these 7 bits, right, 6 through 0, is going to be joined with a 0 on this side, right? Because that 1 tick mark B0 is to the right of these 7 bits. So it's going to take these 7 bits and put a 0 on this side. So effectively, what is it doing? Like, which one of these 4 things is it doing? Taking these 7 bits and you're putting a 0 on this side. So it's now going to become 8 bits. What's going to happen to these 7 bits if I put a 0 there? They're all going to go over one place, right? So what is that? Which out of the 4? Shift left. Yeah, it's a shift left. See, this is the System Verilog code that models a shift left. Okay. And if your select is a 3, well, look what's going to happen. It's going to take bit 7 through 1. So it's going to take these 7 bits and it's going to put a 0 on this side. Right? You can see how the 1 tick mark B0 now is on that side. So effectively what happens then? Which one of those 4? Yeah, that's a shift right. So you see the code in System Verilog to do a shift left or shift right. You're using that concatenation, right? The joining. All right. There is no case 0. Why is that? What are we creating by not having that option? Memory, exactly. See, that's the storage. See, this is going to create a latch. Right, this is when next state of Q is going to equal present state of Q. That's when the storage is happening. So just like if you leave out an else in an if statement, it creates memory. If you leave out an option in a case statement, that creates memory. Okay. I thought you had a question. I thought I saw your hand going up.
Did you leave out any option?
Yeah, if you wanted to make, you know, by doing this, you're making when the select input the 0, the storage. But you know, if you left out say 2, then when the select is a 2, that would be the storage. So yeah, it could be any of these options. Whatever option you leave out, that becomes a storage option. Yeah. Okay, so now again, the reason why you know, I go over this not only for just, you know, like general information, but this is part of the final project individual. It's part of the 4-bit multiplier. So on Tuesday of next week, I'm going to go into more detail about the final project, and you know, you'll see in more detail how this fits in. Okay, but this is, you know, like the general operation, if you will, of a universal shift register. Okay. All right. So any questions before we go into sequence detection? Okay, because sequence detection is lab 6. Okay, in lab 6, you design and build in System Verilog a sequence detector. Okay, so I'm going to go over what sequence detection is. I'll give you an example of a sequence detector, and you know, if everything makes sense about all this, there's something I forgot to erase. So sorry, that shouldn't be there. Then you should be able to do lab 6. Okay. All right. So first thing about sequence detection is that there's 2 types of sequence detectors. Okay, one type is called resetting. And what's meant by resetting is that after a detection, no bits of detected sequence can be used in a subsequent detected sequence. I know it's a lot of words. I tried to think of ways to make this not as wordy, but I haven't thought of one. This is the best I can do. So after detection, no bits of a detected sequence can be used in a subsequent detected sequence. Okay, that's what's meant by resetting. Non-resetting is the other one. Okay, so there's resetting and there's non-resetting. Okay, non-resetting, after a detection, bits of a detected sequence can be used in a subsequent detected sequence. So the non-resetting in words, same words as the resetting, except you don't have no here, right? Because resetting, after you have a detection, you can't use any of the bits of that detected sequence in a subsequent detection, where in non-resetting, you can use the bits of a previous detection in a subsequent detection. Okay, that's the difference between the two. Now we're going to do some examples here, and hopefully these words become more clear. Okay. All right, so here's an example to show the difference between a resetting and non-resetting. So let's say we're looking for this sequence. Okay, we're looking for a 1, 0, 1, 1. And this string of zeros and ones is just, you know, this is t equal to 0. And as time progresses, this is our string of ones and zeros that we're looking for this sequencing. So if it's resetting, okay, we'll do resetting first. I would detect 1, 0, 1, 1 there, right? That would be a detection. Then I would have a 1011 there, that would be a second detection. Then I would have a 1011 there, that would be a detection. But now, if it's resetting, you see right here, I have a 1011 again. But because this one is part of a previous detection, that would not be a detection for resetting, because you can't use any bits from a previous detection for a subsequent detection when it's reset. Okay, so for resetting, we would just have 3 detections. Okay, if it's non-resetting, I would still have this detection, I would still have this detection, I would still have this detection. But now if it's non-resetting, because I can use bits of a previous detection in a subsequent detection, I would have a 4th detection in the non-resetting case, because I could use that one for this 4th detection. All right, so you see that's the difference between the two. Does everybody see that? Okay, we're gonna do more with this, so you know, you're gonna see more about the difference coming up, but everybody okay up to this point? All right, so the next thing, and this is really where you would start your lab 6, okay, because you're gonna design in lab 6 an FSM that does sequence detection. And remember, we talked about FSMs last week. And what's always the first thing that you do, that you draw before you try to write any type of system Verilog code to model an FSM? Like, where do you always start? What drawing do you always start with? Well, you need a black box diagram for like the main inputs and main outputs, but what other diagram do you need to actually model the code that we had on the board last time that had the always comb portion and the state diagram, right? You always start with the state diagram, because remember, once you have a state diagram, to go from the state diagram to the system Verilog code you need to model that FSM, it's fairly cookbook, right? I showed you the format last class, right? Like you define your states, and then you have your always FF for the memory portion, then you have your always comb for the decoder part, okay? So yeah, you always start with the state diagram when you do an FSM design. Let me turn the camera. And all state diagrams need to have a legend. Yeah, I think there was a few groups. Now I'm talking about all my sections here, not just your section. I think there was like a few groups. I don't know. I don't remember if there was any in this section, but there was a few groups that either missed putting the legend on the activity, or they didn't have like a specific legend. They had like a generic one. But yeah, make sure in any state diagrams that you turn in, because you will have to turn in state diagrams for the final project, that you have, you know, a legend that's specific to the diagram, you know, that not something general. So just as a little review of the symbology here, in a state diagram, what does the circle represent? Right, that represents a state. What does the arrow represent? What? Clock, yeah, clock transition, exactly. Either rising edge or falling edge, depending on which one you have. This Z, what is this Z? What do we put here? Okay, what kind of output? Right, that's your more output. Okay, remember, if it's a more output, the reason why we put it within the circle is because the circle represents a state, and the more output only depends on the state. Now, X here is an external input. Okay, so this is an external input. Okay, that's going to be the string of zeros and ones. Okay, that we're looking for, you know, a detection, you know, looking for a sequence in. This state diagram does not have a mealy output. If it did have a mealy output, you know, you'd see a line here with some variable under the external input. Okay. All right, so let's go ahead and create the state diagram for this sequence detector. So in my state diagram, you can see I have 5 states and I labeled them. Oh yeah, remember this is the label, right, where I have state here. That's just a label. So I just call these, you know, letters, as you can see. And we're gonna start with state A. That's where my state diagram is beginning with, this state A. Now, the other thing you need to know here is that this more output Z equals a 1 when sequence 1011 has been detected. Okay, otherwise it's 0. Okay, otherwise Z equals 0. Okay, so that more output, that Z more output, it's only going to equal 1 once we've detected the sequence we're looking for. Okay, otherwise it's just going to be a 0. So here in the state that I'm starting at, state A, well, clearly Z is going to be 0, right? Because we haven't even started to find our sequence yet. Well, let's say that the first bit that we get is a 1, okay? Which is what we're looking for, right? We're looking for the first bit to be a 1. Well, if I get a bit that's in the sequence I'm looking for, I'm just going to move to the next state, right? So you see, if I'm in state A and I get a 1, I'm going to go to state B. Now, we'll come back and talk about where we would go if we get a 0 when we're in state A, but we'll do that in a little bit, okay? All right, so now we're in state B. Z is going to be 0 because we haven't detected 1011 yet. When I'm in state B, if I get a 0, I'm going to move to the next state because that's part of the sequence I'm looking for. Okay, and when we're in state C, again, we haven't detected our sequence yet, so Z is still going to be 0. Now, also what I'm going to do here, now, what I'm about to do next is not required. Okay, it's not like an official part of a state diagram. But I'm going to do the next thing because it helps determine where you go if you don't get a bit in the sequence you're looking for. So what I'm going to do here is I'm going to write next to state B, C, D, E. I'm going to write what it took to get to that state. Right? To get to state B, we needed a 1. To get to state C, we needed a 1, 0. Okay. All right, so now we're going to continue. I'm in state C. If I get a 1, well, I'm going to move to state D because that's part of the sequence I'm looking for. When we're in state D, we haven't detected the sequence yet, so Z is still at 0. And to get to state D, it took a 1, 0, 1. Okay, now if I'm in state D and I get a 1, I move to the next state E. And once I'm in state E, I have a detection, right? Because now I've detected 1, 0, 1, 1. So Z becomes 1. Okay. And to get to state E, it took a 1, 0, 1, 1, right? It took the sequence I'm looking for to get to that state E, right? Because that's when I have the detection. Okay. Oh, and let me write here, I forget to write a 1. Okay, so everybody see what we're doing so far? All right, now it gets a little tricky. Okay, now we got to figure out, well, where do we go for each of our states if we don't get the bit we're looking for? Okay, so let's go back to state A. Okay, again, this is where we're beginning. State A, if I get a 1, I'm going to move on, right? Because that's the first bit I'm looking for. But what if we get a 0 first? Instead of getting a 1, what if we get a 0? Stay there. Yeah, we just want to stay in state A, right? Because we would just stay there until we get a 1, right? So you see, we would just stay in state A if we get a 0. All right, now, how about state B? State B, if I get a 0, I move on, right? Because the 0 is part of the sequence. But where would I go if I get a 1 and I'm in state B? State A. Would I go back to state A? Any other ideas?
Stay in state B.
Stay in state B. Any other possibilities? Anyone thinking something else? How many people say state A? How many people say state B? How many people don't know? How many people want to go home? No, can't do that. We would stay in B, right? And the reason we would stay in B is just think about it. You know, if we get a 1, right? The first one's a 1, we go to B. Now, if we get another 1, well, we would just stay there because it's possible the next bit would be a 0, and now we've got the first two bits of the sequence we're looking for. So if you're already in state B and you get a 1, you just want to stay there, right? Because it takes a 1 to get to there. So you see, you just stay in B if you get a 1. That makes sense. Okay, so we're in B, we get a 0. Let's see, did I make a mistake here? Let's see, oh no, yeah, we're in B, we moved to C. Right, we're in C now, sorry, we're done with B. Now we're in C. If we're in state C and we get a 1, well, we move on because that's part of our sequence. But where would we go if we're in state C, we get a 0? So remember, it took a 1, 0 to get to state C. So now if I get another 0 like this, I have 1, 0, then another 0, where would we want to go? Stay in state C, any other ideas? State B, any other ideas? State A? How many people say state C? How many people say state B? How many people say state A? How many people don't know? See, this can be tricky. Okay, well, think about it. It took a 1, 0 to get to state C. If I get another 0, is there any way I could get this sequence if I get 2 zeros in a row? No, so if there's no way I can get this sequence, where do I want to go? Back to the beginning. You want to go back to A. Right, because if I get 2 zeros in a row, there's no way now I can get a sequence from, you know, anything I've had, right? I just basically got to start over again.
Oh, it's so the reason that you can stay in state B because we have a section with 2 1s in a row. But
Right.
then if we got 3 1s in a row, we would have to.
No, it doesn't matter. If I just got a whole string of 1s, right? I would just keep staying in B because if I then get a 0, I can move on, right? Because that would be the first 2 bits of what I'm looking for, right? Because I'm looking for this. It doesn't matter like what's before the beginning of the 2 bits I'm looking for, right? As long as eventually I get that sequence. Or does that not help? Yeah, it's tricky. This gets a little, yeah, it gets a little getting used to. You gotta, I think, practice a little bit. But again, I think that's where writing down what it takes to get to a certain state will help. Right? Because again, if you're just in state C, it took this to get there. If you then get a 0, well, 1, 0, 0, you'll never get this sequence. So that's why you got to start over again. But if I'm in state B and it took a 1 to get there, and I get another 1, well, I just stay there, right? Because it takes a 1 to get there. And it doesn't matter how many 1s I get. Eventually, if I get a 0, I would move on to state C because then I would have a 1, 0. Okay. All right, so let's see. So we got C. Now we move over to state B. In state B, it took a 1, 0, 1 to get there. If I get a 1, well, then I have my detected sequence. Where would I want to go if in state D I get a 0? So I'd have 1, 0, 1 because it took that to get there, but now I get a 0. Back to state C. Yeah, exactly. You would go to state C because it takes a 1, 0 to get to state C. So see here, we would just go back to C. Okay, so, you know, these state diagrams, they are tricky. You know, they are tricky, but again, I think it helps if you write what you know, what sequence you have to get to that particular state, because I think that helps with determining where you have to go if you don't get the next bit in the sequence. Okay, so now I'm going to ask you a question, and before I ask you that question, I want to remind you of the difference between resetting and setting. Okay, remember, resetting after a detection. This is very key. After a detection, no bits of a detected sequence can be used in a subsequent detected sequence. Okay, non-resetting, same thing. After a detection, bits of a previous detection can be used in subsequent detection. So now the question I want to ask you is, what I've drawn thus far, okay, All this leads up to a detection, right? We don't have a detection until state E. That's when we have a detection. So my question to you is, what I have drawn on the board here, is this resetting, setting, or both? Like what I've drawn here, is this good, whether it's, is this good only if it's resetting, only good if it's non-resetting, or is it good for both of them? Both. Why? Look at the definition. What's the first three words in the definition? After a detection. See, before you have a detection, there's no difference between these two. So the state diagram, whether it's resetting or non-resetting, it's the same. What can be different is after you have a detection. We don't have a detection until state E. Okay, so when we finish this, right, when we finish this from state E, you'll see there is a difference between resetting and non-resetting. But up to that point, up until you have a detection, the state diagram for both of these is going to be the same. Okay, the reason I harp on this is a common misconception. You know, people think that the resetting and non-resetting have different state diagrams before there's a detection. You know, you'll see in lab 6. In lab 6, we want you to do a resetting state diagram. But occasionally I'll have students that'll be like, oh, I have this state diagram for my resetting, but I'm just wondering, what would the state diagram look like for the non-resetting case? And I go, basically the same. You know, it's just going to have a little difference perhaps at the very end after there's a detection. Okay, but sometimes people think there's like a big difference between the two. Okay, but there's not. Okay. All right, so hopefully you've driven home that point. So now we're going to finish the state diagram for both cases. So we'll start with resetting. We'll do resetting. Let's see, we'll do resetting in blue. Okay, so we're going to do resetting in blue and non-resetting in green. Okay, so let's do resetting first. So we're in state E, right? We have a detection. Let's say we get a 0. Okay, so we have a detection. We're doing resetting. We get a 0. Remember, resetting after the detection, you can't use any previous bits in a subsequent detection. So if I get a 0 after I've had a detection for the resetting, where would I go from state E? And I'm still looking for 1, 0, 1, 1. Yeah, you just go to A, right? Because the first bit in our sequence we're looking for is a 1. So if we get a 0 to start with, we just go to the beginning, right? So we would just go to A if we get a 0. Okay, what if we get a 1 after detection and it's resetting? And again, I can't use any previous bits. So I'm in state E and I get a 1. Where would I go? What did you say? B? Everybody agree? What does it take to get to B? A 1. So that's where we would go, right? See, so we would go to B if we're in E doing a resetting. Okay, so the black with the blue would be the total state diagram for a resetting case. Okay, so any questions on that before we talk about non-resetting? Okay, non-resetting. Let's do 1 first. Okay, non-resetting. I have a detection, then I get a 1. Now with non-resetting, I can use bits from a previous detection for a subsequent detection. And we're still looking for 1, 0, 1, 1. So where would we go? Yes. It'd still be B, right? Because again, it takes a 1 to get to B, right? That could be the start of another sequence, right? So you see, this would go to B if it's a 1. Okay, how about this? Okay, non-resetting, we have a detection. Now I get a 0, and remember, non-resetting, I can use previous bits for a subsequent detection. We're still looking for 1011. Go to C, exactly, because now I can use this 1 in the next sequence. So I would go to the state where it takes a 10 to get to. So I would go to C, right? Because it takes a 10 to get to C. Okay? So what you see in black and green, that would be the state diagram for the non-resetting case. Okay? Yeah, I think if you can do a state diagram for a sequence detector and you can build that in System Verilog, like you have to do for Lab 6, you can handle any FSM. The FSM in CP233 and that microprocessor is not as complicated as these sequence detectors. It's actually fairly straightforward, the system diagram or the state diagram. Okay, so this is probably the toughest state diagram you're going to see in Lab 6. Because Lab 6, and I'll talk about it in more detail coming up. But Lab 6, we asked you to build an FSM sequence detector that can detect 2 different sequences. Okay, one sequence when a button is pressed, the other sequence when a button is not pressed. Okay, and we'll talk about that in more detail coming up here. In fact, that's the next thing, as long as you don't have any more questions about how I did this. Okay, I admit it's a little tricky, take some practice, but again, try writing out what it takes to get to a particular state, and I think that helps determine where you have to go when you don't get a bit in the sequence you're looking for. Okay. All right, so let's talk about Lab 6, and for that, there's some stuff on Canvas I want to show you. Computer. So again, I realize that the resolution isn't good, that you can't really see the text here, but this is on Canvas, so you can bring this up on your computer and just find where Lab 6 assignment with diagram, that PDF is at. And this has the instructions for Lab 6. If you look at the diagram here, there's 4 modules, but 3 of these 4 modules are provided. Okay, this is a clock divider module. This is a sequence driver, and I'll explain what it does coming up. This is named BCDEC. Again, I'll explain coming up. But these 3 modules were designed by Dr. Mealy, and they're provided. They're written in VHDL. Okay, you may remember from Lab 5 that time multiplexer that we give you from Dr. Mealy. It's written in Verilog, and Vivado can run mixed languages. Okay, so same thing here. Even though VHDL is a different language than System Verilog, Vivado, it's no problem. It can run mixed languages. Those files that you need, those 3 files, they're also on Canvas. If you go to Lab Resources, same place where the text file for the universal seg is. Okay, this is what you need for Lab 5. These 3 files here is what you need for Lab 6. And these aren't text files, these are actual VHDL files. So you just have to download them and put them into your project. Okay. So you're told that there's 2 sequences. One sequence is 011001, and the other one is 011. Oh, I guess this one's 0111101, and this one is 01001. But these 2 sequences, they only differ by 1 bit. Okay, the 4th bit is the only bit that's different. All the other 5 bits are the same. Okay, and you can see here that your FSM has a button input. So, there's those 5 buttons that are on your basis board. So when a button is pressed, it outputs a 1. When it's not pressed, it outputs a 0. So when the button is pressed, you're looking for one of these sequences. When it's not pressed, you're looking for the other one. Okay. So your state diagram, there's actually 2 different approaches to the state diagram. Some people will do 2 separate state diagrams, like this is the one for the button pressed, this is the button, or the one for the button not pressed. And then they just connect them together with, a variable button. Like if it's 0, I go to this state diagram. If it's 1, I go to this state diagram. Other people, and this is what I did, use one state diagram where that state diagram has 2 external inputs, button and X. Okay, X is the string of 0s and 1s where you're looking for the sequence. And in the state diagram is going to be the same until you get to the 4th bit. Right, then it's going to branch depending on what the button is equal to, and then it comes back together. Okay, so you can either do it in one state diagram or 2 separate ones that tie together with the button input. Okay, let's see. The other thing is we want you to do a resetting. Somewhere in here it says resetting. Okay, so remember, resetting means you can't use any bits of a subsequent detection or a previous detection for a subsequent detection. Now, what these modules do, first of all, we have a clock divider, okay, this module right here. And we talked about the purpose of a clock divider previously. Like, what does a clock divider do? What's its purpose? Yeah, it's just cutting down the frequency of the clock, okay? So that's exactly what this is doing. Now, notice that the slow clock, right, the output of the clock divider, it goes to the sequence driver, and it goes to the FSM. BCDEC, okay, this module over here, it operates off the fast clock. Okay, so make sure that you connect the fast clock to BCDEC, because a common error that people make is they connect the slow clock to BCDEC, and if you do, it's not going to work. Okay, it's designed to work off the fast clock, and I'll explain what it does coming up. All right, so you got the clock divider, then you have the sequence driver. The sequence driver module, the input is 8 bits, it's 8 switches, and its output is a single bit. So what the sequence driver is doing, it's taking the data that the switches are giving and putting it on one output, so that data is now separated in time. So basically, this is what's called a parallel to serial data converter, right? That your switch data is parallel because it all has, like, each bit has its own wire. That's what's referred to as parallel data. What's coming out of the sequence driver is you got that same data, but now it's on one wire, the output. So that data is separated in time. So it's gonna, you can think of it just like this, that it's just a string of 0s and 1s. This is t to the 0, and as time goes on, it's going to be changing, and it's going to represent the data that the switches are at. Okay, and you see the output of that sequence driver, it goes into your X input of your FSM, right? So your FSM is going to be looking at what's coming out of that sequence driver and looking for the sequences to detect. Okay, again, based on the button position, right? And then the output of your FSM is just a single bit output. It's going to be a Z output where it's a 1 if you detect the sequence, it's a 0 if you don't detect the sequence, and that goes to a single bit input of BCDEC. BCDEC is another time multiplexer, but what's different, the main difference between BCDEC and the universal seg, universal seg is putting, binary information onto the 7-segment display, right? Because it's taking the binary that's on that count 1 input. Here, the BCDEC, if Z is a 0, it's going to display crap. If Z is a 1, it's going to display cool. Okay, so when you get a detection, your 7-segment display should change to cool. Okay, why Dr. Mealy decided to use those words, I don't know, but that's what it is. Also, there's this LED output. Okay, 15, or no, I think it's 8 LEDs. In a video that I'll show you in just a moment, you'll see the purpose of the LEDs. Okay. Now, there's a few things I wanted to make sure that I mentioned, because if I don't look at this, I usually forget. All right, I already mentioned about the lab 5 buttons. I did that at the beginning of the class. Okay, here we go. All right, another important thing. Okay, because this, again, this is a common mistake people make. Even though I understand the reason why they make it, it's still a mistake. And that's, every quarter, there's a few students that they look at this, they see that it's got to be resetting. And they automatically think, oh, there must be a reset input. Okay, and then they go ahead and they add like a reset input. There is no reset input because again, resetting in this context does not mean like resetting for a flip-flop or a register. Okay, it means what we talked about before. Okay, so do not add a reset input. Okay, another thing is, okay, and this goes back to lab 5 because the same thing applied in lab 5. Lab 5, where we're using that time multiplexer that Dr. Mealy designed. Remember last week when I talked about that module, remember how I said the simulation can't, or the simulator in Vivado cannot simulate time multiplexing. So the output of the universal seg, when you look at it on the timing diagram, when you do the simulation for the overall, it's just going to be garbage. It doesn't mean anything. You shouldn't even look at it, okay? So what did I say last class? What do you have to do for lab 5 to verify that your overall design is giving a good simulation, that your timing diagram is correct? What do you got to look at?
Pull out the internal signals.
Yeah, you got to pull out the 3 inputs going to Dr. Mealy's module. There's, the 4-bit number, there's the validity bit, and there's the sign bit. So those 3 inputs you have to put onto your timing diagram. And if what's going into Mealy's module is correct, then it should work on your board because we know Mealy's module works. Okay, because we've used it for years, it works. Okay, well, similarly, in lab 6, this BC deck module, it's another time multiplexer. So you will not be able to look at the overall to verify that it works because when you look on the timing diagram at the outputs of the BC deck, it's not going to make any sense. So lab 6 is different than the previous labs because the previous labs, you would turn in the simulation for the overall design. Here, you're going to turn in the simulation for your FSM because everything else is a Mealy module. And again, we know they work. So if your FSM is good and provided you made the connections correctly, your overall should work. Okay, so what you turn in for your simulation for lab 6 is the simulation for your FSM. Okay, that's the timing diagram you would show. Okay, let's see, what else is there? Oh, now you will have to make one modification. Okay, you're going to have to make one modification to this clock divider, and I'll show you the reason why in a video. So let me show you this video. This video will show you what the sequence detector should look like on the board if it's working. So if you go here to meeting 14, this link. Okay, so if it hasn't detected a sequence, it has crap, and then you see the LED shows you which switch data it's looking at. Okay, so you see once it's gone through and it makes the detection, it changes to cool. Now, in this video, I don't show all the test cases. I show 3 of the 4. There's one missing. So when you do yours, make sure you do 4. Okay, so here I change a bit. So now it won't detect it when the button's not pressed. Okay, the first was a detection with the button not pressed. This is no detection with the button not pressed. So notice the rate of the LED here. Okay, now it's going to detect it because I pressed the button and I have the sequence for the button pressed in. Okay, so like I said, I showed 3, it's just repeating now. I showed 3 of the 4 test cases, but that's what it should look like. Now, the modification you have to make in the clock divider is that there's an integer, just like in that example I showed you last class when I showed you the clock divider. Remember there was that parameter max count? And depending on what that max count number was, that would determine what the frequency coming out is. Okay, well, in Dr. Millie's clock divider module, he has an integer. Now, I forget what he calls it. He doesn't call it max count. But when you look at the code, you'll see a number that's like 3 million. You have to change that number to something greater to get the speed of the LEDs and also the speed of when it changes from craft to pool to look like what's in this video. Because if you use the number that he has, you'll see that these LEDs go really fast. And when it changes to cool, it does it like so fast, you can't even really notice. You just see something change, but you can't even tell it's cool, okay? So you're gonna have to go in and just make that one modification in the clock divider, you know, change it to like 30 million instead of 3 million, something like that. And just make sure that it looks something like this. It doesn't have to be exactly, but make sure it's not really fast. Okay? All right, the last thing is there's a typo on the activity that you have. So on each table, there should be enough activities for everyone. So if you want to take a look. So if you take a look at this activity, there's 2 tiny diagrams that I want you to fill out. This is a universal chip register. Okay, both of them here. So the typos are, you see where it has select is equal to 1, 0, right shift, DL in, that should be DR in. So change the L to R. And then right below it, where it has select equal to 1, 1, left shift, DR, that should be DL. Okay, so change DL to DR and DR to DL. And then in the timing diagram, and this goes for both of them, where it says DR in, make that DL in. And where it says DL and make that DR in. Okay, so there's 4 typos, right? 2 up here and 2 in the timing diagram. So did everybody get that, or do you want me to repeat it? Everybody's good? Sure. Up here where it's select equal to 1, 0, right shift, make that DR instead of DL. And then right below it where it says select equal to 1, 1, left shift, make that DL instead of DR. And then in the timing diagram, both of them, change DR to DL and DL to DR. Okay, if you do that, then your answer should match my solution. Okay, and I have it posted on the board over there. Okay. All right, so do you have any questions? Because if not, work on the activity. Once you're done with the activity, you should be working on, oh, wait a minute. I got to talk about the class schedule. I'm sorry. Sorry, I'm getting so excited that you want to start your activity. Forget about the class schedule. So yeah, I just wanted to go over the class schedule for the rest of the quarter. Because I made a few changes, so I just want to make sure you're aware of the changes. Okay, so I would take a picture of this at some point, just so you know you have it somewhere and you can refer to it. Okay, first thing, class this Thursday is canceled. I have a medical procedure on Thursday, so I'm not going to be able to come to class that day. Now I'm going to talk to the ISA. I'm going to talk to Ratchet and see if he wants to be here for at least some of the time. But there is no class that day, so you're not required to be here. And don't feel bad because we had an extra meeting this quarter because we started on a Thursday. So you're not losing any information. You're still getting, you know, what everyone gets when they take this class. So it's not like you're missing out on anything. Now, the other thing, I changed the due date of lab 5 to Monday instead of this Friday. And the reason being that this Friday, and I wasn't even aware of this until I looked this weekend. This Friday is a holiday. Okay, it's Veterans Day, so you don't have any classes that day. So because it's a holiday, lab 5 is now due on Monday, the 13th up here. Now, lab 6 is still due on Friday that same week, the 17th. And the reason I didn't change that is because that's the Friday before Thanksgiving break. And I want you to be done with the labs before the break. That way, when you come back, you just concentrate on the final project. Okay, so basically you're gonna have 2 labs due next week. Lab 5 on Monday and lab 6 on Friday. Okay, another change is, you know, my office hours have been on Wednesday And I'm still gonna have office hours tomorrow. Okay, tomorrow's Wednesday. But next week, I can't have my office hours on Wednesday, because again, I'm gonna be obligated to do something else, so. My office hours next week is gonna be on Monday. Okay, the 13th, in the same time, 10 to 3, okay? Okay, the last in-person meeting we have, because remember, at the beginning of the quarter, and I have this in the syllabus, you know, this is what's called a blended course. The first 15 meetings are in person. The last 5 are, you know, I call them online, but really it's just, I'm available on Zoom as you work on your final project. Okay, and Tuesday, November 14th, so Tuesday of next week, the last in-person meeting we have, I'm gonna talk about the final projects. You know, the final project has 2 parts, an individual part and a team part. Okay, and I'll talk about those. I'll also have your midterm scores. I didn't quite finish grading the midterms over the weekend. I'm about 80% done. So I'm sure I'll have them that Tuesday. I'll have your scores. Also, let's see, what else? Okay, Thursday of next week, that's an open lab. So what I mean by open lab is there's no lecture, no activity. I'll be on Zoom. You can come here if you want. You're not required to. Again, I'll talk to the ISA Ratchet, see if he'll be available that day. That way, if you do come and you need some help, he'll be here. But again, I can give you help over Zoom also. Now, one thing I wanted to mention about this, and you know, remember, I have 3 sections. I have, you know, 80 some odd students. And there's a very small percentage. I mean, most students have been keeping up with the lab work and they've been doing really good on the labs, you know, very good. But there are a few students, and again, I'm talking about all my sections, not just this section, that are behind on the lab or some of the labs. So remember, I have this in my syllabus. I talked about it on the first day. I'm just reminding you that if someone does not complete more than 1 lab, I will not issue a passing grade. Okay, and I don't care how the person did and everything else. The reason for that, and again, I know it sounds harsh, but it's harsh for a reason. CPE 233 is very lab intensive, okay? And my feeling is that if someone cannot complete more than 1 lab, like I'll give you a break on 1 lab, but you know, 2 or more labs, if you cannot complete them, in good conscience, I can't pass you from this class, because the chances of you doing poorly in CP 233, if you can't do the labs in this class, is pretty high. You know, if you can do the labs in this class, I think it's the other way. It's very high probability that you'll do well in CP 233. Now, what I mean by you don't complete it is, you know, the 5-day late period passes and you never turn it in. You know, if you miss the 5-day late period, you can't get credit, but you can still pass it in to me, so I at least know that you can do it. Okay, so you know, and again, I give 1 pass, but if there's more than 1 lab that a person can't do, like I said, I can't pass that person. Okay. Also, if you haven't completed more than 1 lab, I won't assign you to a project team until you do. Okay, and the reason for that, I think it's unfair for me to match you up with another person if you haven't shown that you can do the lab work yourself, because I think that puts pressure on the other person to do more work. Okay, and then also with the project teams, I allow people to work with whoever they want to work with. Like if you know somebody in the class that you worked with previously and you work well together and you want to be partners for the team part of the final project, just let me know. The best way to tell me is through email, but you can tell me in person. But if I don't hear from people, then I just, you know, randomly team up people. Okay, in the final project team, it's 2-person. Okay, no 3-person. It's up to 2-person. Okay, and I prefer for someone not to do it by themselves. But if somebody wanted to do it by themselves, because occasionally somebody will want to do something really ambitious, so they're going to end up doing all the work themselves anyway, and they say, can I just do it myself? In a case like that, that's okay. But you know, under normal circumstances, it's best to have 2 people. 3 people are too many, and usually 1 person, unless they're very ambitious, it's too much for 1 person. Okay. Let's see, what else did I have up here? So, you know, then we have our break, 18th through the 26th. During the holiday break, I'm going to be away most of the time. If you email me during the break, you know, I will respond as quickly as I can, but it may be a few days depending on where I'm at. Okay, so I'm not Like I said, I'll do the best I can, but don't expect like a real quick response if it's during that holiday break. Okay, week 9, no in person, like I said, I'll be available on Zoom. The file project individual is due on Friday, December 1st. That's the Friday of the 9th week. And then the team part of the final project, that's due the Friday of week 10, which is the last class day, which is Friday, December 8th. And I'm gonna talk in more detail about this on Tuesday. And then remember, there is no written final exam. So this class ends on the last class day. It ends on December 8th. Okay, we don't have anything during final. Okay, because the final project is the final. Okay, but
During that time where you're gonna be on Zoom, will this room still be open?
yes. Yeah, this room will be open, and remember, even if it's not, we got the code there. So as long as you have the code, you know, you can unlock the door that has the. Oh, you didn't know that? Yeah, I talked about that on the first day. It's been up there all quarter.
I mean,
But yeah, you can come here, yeah, during the times that I'm on Zoom. Okay, all right, so any questions? If not, you should be able to do the activity now. Once you're done with the activity, work on whatever lab work you need to. And Racket's gonna be here at 5 to help out.